From now on, we're going to talk about weight initialization and other techniques for optimization. Let's recap what stochastic gradient descent was. Stochastic gradient descent looks like this. The first step is initialize weight and then pick learning rate and then mini batch size. And in the second step, we draw mini batch. And for all elements of mini batch, we do forward propagation, calculate loss. And then using this loss, we calculate gradient using the backpropagation process and update the weight using our gradient. And if this process is not enough to make our AI models strong, then we go back to the second step and repeat these processes. And up to this point, we've discussed mini batch size and other factors, but we never discussed how we choose the initial weights. How do we initialize the weight for our models? The simple solution is, what about setting all network parameters to a constant, for example, 0? What happens in this case? In this case, learning might not be possible because all units of each layer are learning the same thing. They receive the same gradient because they have the same parameters, and everything learns the same thing, and not enough information can be extracted from the inputs. Therefore, this is not a good idea. And when we consider a layer in multi-layer perceptron, this is the net input, an activation function, and the loss looks like this. We apply chain rule to calculate the loss in respect of the current parameter. And for activation function, in this session, we're going to use hypertangent and ReLU. For hypertangent activation function, let's assume that we draw weight independently from Gaussian with small standard deviation, like 0.01. Then the activations in deeper layers tend towards 0. In the first layer, the weights are distributed quite well because you are drawing these weights from Gaussian, and they look like this. However, even though we only go to like layer 3 and 4, they become squashed to have 0 values. And gradient with respect to these values will become 0, meaning that the loss comes from here, and then we need to go back. This is a forward propagation path, and this is the backward propagation path. Because the loss here is 0, gradient flow is blocked at this point. Therefore, our model will not learn anything. And what about drawing weights with large standard deviation, like 0.2? In this case, what happens is weights are skewed to the two ends like this. And local gradients are going to become 0 as well, because all activation functions saturate. And therefore, there is going to be no learning occurring, and we cannot train our network. To solve this problem, this paper, Glorat et al., proposed this idea. What about drawing weights independently from Gaussian, but let's set the sigma, or the standard deviation or variation, as 1 divided by d in. Here d in denotes the dimension of the input. And this may vary across layers. After initialize the weights using this scheme, activation distributions spread well across different layers. This could allow effective learning. By the way, why should we set sigma as 1 divided by square root of d in? Let's consider this simple example. And let's assume that all xi and wi are independent and identically distributed, IID, with zero mean. And let's further assume that g prime 0 equals 1. And we're going to say that the variance of y is similar to variance of wt, w transpose times x. The dot product between the wave vector and the input vector. Here we're just approximating. We're removing this activation function. Then, because the components of W looks like this, and X looks like this. Because these components are independent, we can approximate that the variance of this value is di times din, because we have din elements, variance of xi times wi. And how do you calculate the variance? Variance can be formulated as the expectation of the squared minus the square of the expectation. This is a high school or first year mathematics. So you can expand this variance into this equation. And because we know, we just assume that xi and wi are independent, we can separate this like this. And we just assume that they have, xi and wi have zero mean. So we can remove this part. And this one corresponds to variance of xi. This one corresponds to variance of wi. And the variance of wi equals 1 divided by d in. And the variance between variance y and variance xi becomes equal. This is why we are setting the variance as the square root standard deviation as 1 divided by square root of d in. However, for ReLU activation, it's a little bit different. The Xavier initialization assumes zero standard activation function. However, for ReLU, it is not zero standard. As you guys all know, it looks like this. For ReLU, activations again start collapsing to zero for deeper layers. So as you go deeper, elements tends to gather here. How do you resolve this situation? Since ReLU is restricted to positive outputs, variance must be doubled. That's a simple solution. So rather than drawing weights independently from Gaussian of sigma square 1 divided by d line, we multiply 2 here because we are using just one part, only the positive part. And after that, the distribution becomes well spread. Okay, so data preprocessing is to zero center the network inputs, and decorrelation and whitening are used less frequently. And I showed you that proper initialization is important for ensuring a good gradient flow. And for zero standard activation functions, you better use Xavier initialization. And for ReLU activation, you better use 해 initialization. And initialization is a research topic, and there have been numerous research outcomes. But as we've seen in the batch normalization session, we know that other techniques can reduce the impact of weight initialization. Okay, so up to this point, we've discussed how we normalize batch normalization using batch normalization, and we also talked about weight initialization. And another component we're going to have a look at is learning rate. What was learning rate? Let's have a brief recap. We just calculate the gradient, and then rather than just using the full gradient, we multiply a step size. This is called learning rate or step size. And this controls the degree of update. And in the case of SGD or SGD plus momentum, ADA-grad, RMS-prob, ADAM, all have learning rate as a hyperparameter. And which one of these learning rates is best to use? Think about it for a moment. And the answer is all of these are good learning rates because we have all different situations, and depending on the situation, the optimal learning rate varies. And learning rate decay is one of the most popular schemes or techniques. At this point, the learning rate is decayed, and you can see that there is a big drop of the loss. In the case of ResNet, it multiplies learning rate by 0.1 after epochs of 30, 60, and 90. And why is it so effective? When you see the gradient space or the loss space, you first need to take big steps. This one is not a proper one. Okay. Let's say the gradient space looks like the loss space will look like this. Let's say we are starting from here. In this case, we need to take big steps. However, as we move further, we need to reduce our scope and take smaller steps to move better. If you take larger steps here, then we might end up here. As you can see here, the loss does not decrease that much after a certain point. And by reducing the learning rate, so it's repeating, going to this place and coming back to this place again and again. By reducing the learning rate, we can move forward to this direction. So because the scope is changing over and over, we need to decay the learning rate. Therefore, we can take more accurate steps. So that's why decaying learning rate is so effective. And to reduce the learning rate, there is another scheme called cosine. We just follow the cosine shape like this. And these papers employed this cosine learning rate schedule. And here, I'm using the term learning rate schedule. This is how we are going to change the learning rate as we proceed the training. So this is one of learning schedules. And this was also another learning schedule. Okay, so it looks like this. The loss becomes much smoother. And there is another scheme called linear. We just linearly reduce the learning rate. This paper use this learning rate schedule. And there is another one, inverse square root. Attention is all you need is the paper for transformer. Nowadays, ChatGPT or other applications are using this transformer architecture frequently. And in fact, this architecture is prevailing in all areas like speech recognition, computer vision, and natural language processing. And this paper, this architecture, employed inverse square root technique. And there is another schedule, linear warm-up. At the beginning of the training, we start with a very low learning rate. And then we increase the learning rate at the start of the training procedure. And we follow the learning decay scheme after this point. Why do we do this? This is to avoid the bias that could occur for a couple of first batches. We know that batches have different distributions. And if we set high learning rate at the beginning, this could bias the weights. Therefore, at the beginning, we're taking careful steps. And after taking a set of careful steps, you take big steps from here. So that's why linear warm-up is very effective. Okay, think about this problem and let's check the answer together. All right, what's the answer? The answer is the second one. The first option says learning rate should be kept the same throughout the whole process. This is not true. By reducing or decaying the learning rate over time can improve the performance. Second one, scaling learning rate according to the batch size helps is one of the rule of thumb. This is true. And weight initialization highly affect the flow of gradients. That's why we use Xavier or Hay initialization. And the strategy for weight initialization does not depend on the type of activation function. No. If it is zero standard, we better use Xavier. If it is not, we better use Hay. Okay, so up to this point, we've discussed a lot of hyperparameters. But what are the difference between parameters and hyperparameters? Hyperparameters, let's first talk about parameters. Parameters are weights or biases. However, hyperparameters can be mini batch size, the data normalization schemes, number of epochs, number of hidden layers, number of hidden units. We need to determine which schemes or what numbers to use, how to set the numbers. And all these are types of hyperparameters. And the important thing is, mostly no scientific explanation. This is mostly engineering. Therefore, you need to try many things, perform many experiments, as many experiments as possible, and you can build up some insights. Some professors say graduate student descent. Okay. And what is the best value of k to use, or what is the best distance to use? Told you that these choices about the algorithms are hyperparameters. And these parameters are very problem or data set dependent, and you must try them all and see what works best. So you need to do a lot of trial and error. And how do we set hyperparameters? One of the idea is choose hyperparameters that work best on the training data. However, it always works perfectly on training data, but might not work for test data. Therefore, we choose hyperparameters that work best on test data. This is the second idea. However, if you just use up our test data, then there is no way for us to test our developed AI. And you should never do this. You should never touch test data until you finish developing your models. And you should use test data just for once. You should not use test data more than once. You should never do this. This is very important. Rather, you better split data into train and validation. And this one is better than this scheme. So you set hyperparameters using this validation data, and you don't use this data to update the parameters of your model. And the fourth idea is cross-validation. You split data into folds and try each fold as validation and average the results. So in the first case, the fifth one is the validation data, and use the first four folds as train data and find the best hyperparameters. And in the next iteration, you do the same, but considering the fold 4 as the validation. You repeat this process for all these folds and find the best hyperparameter set. However, this is not very common or frequent in deep learning. We just have one type of validation like this. And if it works, then it is highly likely effective for test data as well. Because we are using big data, just validating once is enough. But as stated here, if you have very small data set, you better use cross-validation. And for big data, this process is not feasible because to train ChatGPT, it takes like 30 days, at least 30 days with 1,000 GPUs. And you can repeat this process multiple times. So this is not very common in deep learning. Okay, that was hyperparameters. And from now on, let's talk about debugging tips. When you develop your AI models, you might run into errors a lot of times. And there are many debugging tips, and I'm going to share some of them. And you can have a look at this type of blocks, 37 reasons why your network is not working, like this. The emergency first response is start with a simple model that is known to work for this type of data. And use standard laws if possible. The takeaway lesson from here is that don't try to design complicated model from the beginning. However, start from a very simple model that is known to work and add additional designed patterns or techniques and verify each part as you move on. This is like modular modularizing your implementation. And turn off all bells and whistles, like regularization and data augmentation. And then test which one is working. And if you are fine-tuning a model, double check the pre-processing. It should use the same data pre-processing as the original model in your model. And sometimes the input data might not be correct. And start with a very small data set and check if your model can overfit to this small data set. And gradually add more data. If you can overfit your model to a small set of data, that means your data is capable of learning that type of data. And start gradually adding back all the pieces that were omitted, like augmentation, regularization, custom loss functions. Try more complex models. And there might be some data set issues. Check your input data. For example, the width and height might be mixed up. So for the position of width, you might have fed height. This could happen. Therefore, check your input data again and try random input. If this produces the same results as normal or correct input data, that means something went wrong in the middle. In this case, you need to verify layer by layer. And your data loader might not be correct. Therefore, after you develop your data loader, you just need to visualize or verify the data this data loader is taking, and then use this data loader for training your model. And make sure input is connected to the output. You might not feed anything to your network, but you still could get some outputs. And there might be some noise in your data set, so be careful about that. And you need to shuffle your data set, because if you don't shuffle your data set, your model could memorize the order, or it could have some bias. Like the first 10 images have label ones, and the second images, like the first batch and the second batch, might have labels of 2. And we want to avoid this situation. The distribution among batches are very, very distinct. To avoid this kind of situation, researchers have developed techniques like batch-NOR. But inputting data in this way is reversing the idea of batch-NOR. Therefore, try to mix your data and then feed those mixed data into your network. This corresponds to reducing the class imbalance as well. No, this is not the same one. Let's say there are like, let's say we have only 2 classes, but we have 10,000 images for A, but 50 for B. In this case, our neural network might just say, oh, every image is in the class A, because even though it does that, the accuracy is like this. 10,000 divided by 1,050. Therefore, our model will not try to learn this, but only say the output should be always A. Therefore, you need to reduce the class imbalance. And you need to verify the number of training examples. Often, people say you need 10,000 images per class or more. If you do not have enough data, then our network might not be able to learn anything. And this is explained in the previous slide. And first, use a standard data set and verify your architecture is working, and then move on to your data set. And there might be some problems with data normalization or augmentation. Standardize the features and check if you employ too much data augmentation. If you use too many data augmentation techniques, then the semantics in the input data might be lost. And check the pre-processing of your pre-trained model. You should use the same pre-processing as the pre-trained network. And pre-processing for train, validation, and test sets should be in harmony. And there might be some problems with implementation. Deep neural networks are part of AI, and AI is part of software. And for developing software, we need to take software engineering into account, like modularizing, clean code, and other things. Therefore, try to make clean code and develop the AI models following the software engineering processes. So try solving a simpler version of the problem and then move on to the bigger one. And make sure your training procedure is correct. Sometimes you forget toggling chain validation mode. And some modules have different behaviors in chain or validation mode. And when you develop your own loss function, you need to verify your implementation at least several times. Or sometimes you ask your coworkers to verify your loss function. Because if you use your own implementation, it might contain some bugs. And you also need to check the loss input. Like, for example, cross-entropy loss might take in logits or softmax outputs. You need to check the document and see what this loss function is accepting. You also need to adjust loss weights when you are employing several loss functions. And you better monitor other metrics as well, other than loss. And you also need to visualize other results. Therefore, other results might ring the bell that the training process is not going well. And this is similar to developing your own loss function. You need to test a lot any common layers. And check for frozen layers. Let's say your network looks like this. If you freeze this part, the gradient might not flow this way. So you need to check your frozen layers. And sometimes underfeeding or overfeeding could occur. Therefore, you need to set the network size with the proper one. And hidden dimension errors, you also need to think about it. The dimensions might go wrong. So you need to check the dimensions and explore gradient checking when you're developing your own modules or layers. Okay, and there might be some training issues. This one is repetitive. You need to solve for a really small data set first and check weight initialization. And try changing your hyperparameters if they are not working well. at the beginning, don't employ too many techniques, but start with a simple one. Sometimes you better give more time because the loss might take some time to reduce. It could go this way. So you need the network would need some time. And switch from train to test mode. I mentioned this before. And I talked about it. Visualize as many things as possible. Then you can easily notice if something went wrong. Okay, I already mentioned these. And you also need to change your hyperparameters, such as learning rate. And when you're developing your AI models and actually do some coding, you might see a lot of nans, not a number. I've seen like thousands or millions of nans when I was doing my research. When this happens, try to decrease the learning rate, or this could happen from division by 0 or natural log of 0 or negative number. So be careful about the numbers that are going into some layers. And when this happens, you need to evaluate your network layer by layer and see where the nans appear. All right. Now think about this question. Okay, let's check the answer together. The answer is the first one. I talked about it multiple times, like for developing AI models, you better start with the simplest and gradually move on to more complicated model. And for constructing a batch, it is not okay that the batch contains data samples having the same label. We should change the distribution. And we should not apply too many data augmentations because that could spoil the semantics in the original image. And AI models should behave the same in the training and testing mode? No, they could be different. For example, batch mode. Okay, let's summarize this session. In this session, we talked about the motivation of optimization. Optimization is not a simple process because the loss space have very distinctive characteristics according to the application. We need to be very careful in choosing the correct or proper optimizers. So we saw some techniques like SGD and momentum, SGD, momentum, and ADA, broad, and DAM, like this. We discussed a set of optimization algorithms, and we had a look at optimization strategies like data augmentation, learning rate, scheduling, blah, blah, blah. And we also introduced some debugging tips. All right, let's call it a day.